Typically, the first chemistry we learn about carbonyl groups is where the carbon atom of the CO double bond acts like an electrophile. But there's another huge category of carbonyl chemistry applicable to every carbonyl with a hydrogen next to the double bond. I'm going to call that beta here. Some of the people call it alpha, but it's clearly shown in the diagram. I mean this one here, which I've labeled with the green beta. That chemistry is opposite to carbonyl chemistry, insofar as that carbon can act as a nucleophile. To understand how, we have to understand enol formation. Enols are closely related to enolates. Enolates form under basic conditions. I think it's confusing to teach enolates and enol at the same time. So let me just restrict the discussion here to enol chemistry under acidic conditions. This is intended to be a primer about enol chemistry for the Aldol reaction. To make that carbon into a nucleophile, we have to form an enol. The first step to do that is protonate on the carbonyl. Protonate to activate, that's what I normally say, but in this particular case, I mean protonate to activate the hydrogen on that beta carbon. That's going to leave, and when it does, it generates a CC double bond and an enol. So 2 steps to form an enol. Protonate on the carbonyl and lose a CH carbon from that beta carbon. Enols react with many electrophiles on that carbon. So let me generically imagine an electrophile E plus. When it adds to that beta carbon, the electrons push round and liberate a proton, regenerate the CO double bond, then the electrons flow through the CC double bond, through that beta carbon, and onto the electrophile. Put your pen where the electron density is, that's the OH bond, and push towards the electrophile, and that's E plus in this case. So what have we done? We've got now a carbonyl with the electrophile on the beta position. We've lost a hydrogen from that same position. So effectively, we've done an electrophilic substitution of a hydrogen on the beta carbon. What's the simplest electrophile I can possibly think of? It's deuterium. It's going to seem kind of foolish to say this, but if we substitute our E electrophile with D for deuterium plus a deuteron, then we generate the enol under acidic conditions, remember? And the enol reacts with the deuterium plus on the beta carbon. Now there's 2 more hydrogens on that beta carbon, and they can both leave via enolates. So if we keep, say, shaking deuterium chloride, HCl analog, in an NMR tube, eventually, for a methyl ketone, we will see all 3 hydrogens on that beta methyl disappear and go to deuteriums. If there's only 2 there, 2 will exchange. If there's only 1, 1 will exchange. If there aren't any, none can exchange. There aren't any there. The Aldol reaction is a special case where the electrophile is another carbonyl, specifically an aldehyde or a ketone. And since the enol forms under acidic conditions, and we're putting that carbonyl in under acidic conditions, then it's going to be protonated too to form the most reactive species. Protonate to activate, and this other carbonyl will act as an electrophile. And when it does, we push electrons from the OH again, regenerate the CO double bond through the beta carbon from the CC double bond and on to the aldehyde. That displaces the electrons that were in the pi bond of the carbonyl up onto the OH and neutralizes the charge. So we've neutralized the oxonium electrophile by deprotonating our enol. This gives us a product, which is an aldehyde and an alcohol. So chemists inspired, really. They call it aldol. Even if it's a keto alcohol, it's still the aldol product. Now, there's one thing that confuses some students because the reaction in acid can and often does go further. If the aldol product protonates on the hydroxide group, it becomes a leaving group, and we can eliminate water from that. Probably the neatest way to draw that is to reform the enol and push from the enol, OH, in to form a CO double bond, and then out, but this time to form a CC double bond and push out the water. Enol reactions with a dehydration step are aldol condensations. Why condensations? Well, imagine a cold window and you breathe onto the window. Moisture in your breath will condense on the window. Reactions that give out water are condensation reactions. This is just a primer, an introduction. There are lots of variations, and your prof may make it far more complicated by adding details. But if you understand the basics that I've given here, that takes you at least 50%, maybe 75% of the way. Thank you for listening. Bye-bye, and good luck with your studies.